What kind of probability situation is this?
Compound.
What did you say?
Compound for the third one. Or the second
Compound?
one.
Have we said compound? I can't remember. Compound, yeah, probably, but conditional is better.
Oh yeah.
What's the probability that you're an iPhone user in this data set? Good. And then this one, remember, female, given that you're an Android user. So, yep. Looking at just that category. And there are 5 out of 12 of those. Are being male and using iPhone independent? I'm seeing some nods. Jorge, how do we check for independence?
Pretty sure we multiply by probability A and B.
Here's one of the versions. What do I put here? So, remember to test for independence. Is the probability of A, if we already know B is true, is that the same as just the probability of A if we don't know if B is true? That's the concept behind it. And you could switch those and put B given A and put B in the second. Either one. So, decide which one is A and B. Doesn't actually matter. What do you want to call A and B? Male, okay. So this is male, and this will be iPhone. So what's the probability of being a male given that you're an iPhone user? Male out of the iPhone crew, so 4 out of 11. And then probability of just being male? 11 out of 23. Okay, so how do we check if those are equivalent? Do they look like they are?
No.
Probably not. So this is just under half. This is probably a little bit further under half. But it's probably good to check this one. So just turn them into decimals. So definitely not the same. Question. Let's say this first one is this number, 0.3636. What if this one said 0.36 only? Like just stopped at 0.36.
Yeah.
Would they be the same?
No.
Would they be the same enough? Like think real world. Is 0.3636 significantly different than 0.36? Enough to say, no, they're not independent. I would say no. I would say it's okay to say they're independent in that case. Okay? Real world data is often not just perfect. How'd that go for you? Okay. So keep in mind that we'll probably be ready for our test on Thursday on this whole unit. So if you were gone Friday, we did a bunch of practice on combinatorics stuff. And why don't everybody get this sheet out? If you weren't here and don't have it, come get one. We still didn't get a note in our notes about it, like an example. So we're going to work, this is number 8 from your sheets. We're going to work on that as our example. And this one is a pretty normal example of combinatorics, except for it has this word exactly in there as well. And we're going to look at another version. The next section is another version of exactly. You'll hear that word again. Okay, so let's talk about keywords. What are they?
Exactly.
Good. Probability. Well, random is kind of just part of all of the probabilities, because if we're not doing it randomly, then changes the probability in a way that we can't account for, right? Like if we start accounting for preference, or whatever version of preference, then we can't really do that. So the other word is picked, okay? So picked tells us combinatorics. Okay? And then probability says use the basic equation. Okay. Just want to keep reminding you that you need to identify what you're working with. So probability that 5 are black. 5 are black equals number of ways to choose black. And I'm abbreviating this, so if you don't like the way it is, just add a couple words. So number of ways of black over total ways. Okay. 9 buttons are picked at random. I should probably add in here out of 9. So 5 are black out of 9. Okay, so start with the total. Let's pick a different color for that. That's a suggestion, not a rule, but it just helps frame what you're actually counting. So in this case, what are we counting? Like what is our denominator described as? Not the number, but how do we describe the denominator?
9 buttons picked.
Yeah, how many ways can we pick 9 buttons? Okay. And I think if you're at all struggling with these kind of problems, writing it out will help you. Like a description. How many ways can 9 buttons be picked? Well, is that going to matter what order we pick them? Okay. So probably give yourself that reminder. Okay. Does order matter? And in this case, the answer is no. So, no. So this is how many? 10 and 6. So 16, choose 9. There's our denominator. Right. Now we have to account for the ways to pick black. And this time it says exactly. So how many ways can 5 black be picked? Well, we do need to address this issue of exactly. And we wrote about this just above there. Right here. It says if it asks for exactly account for both the is and is not. And we haven't written this, so I'd like to add that. But what do we do when we have to account for both? We multiply, right? We multiply the is and is not. So where this highlight is, I'm going to put by multiplying. And we'll show it right now. But now you have that. So by multiplying is a little vague. That's okay. So multiply the is and is not counts. All right. What's our question before we even start this? So how many ways can 5 black be picked? What's our first question? Does order matter? Does it?
Yeah.
No. Okay. So we can choose 5 black. Choose 5 black is, what was it, 10? Yeah, 10. 10 C5. And choose 5, sorry, not 5. Choose 4 not black by 6, so 6 C4. Any questions on where those numbers came from? We're picking 9 buttons, so the 2 R's have to add up to 9. We have 10 blacks to choose from, 6 non-blacks. Does it tell us? Brown. Yeah, 6 brown. Okay? You good?
Are you gonna write in the?
Yes, I am.
Oh.
I'm kind of like using all this to set it up.
Okay.
Okay. Like that. Okay, so I kind of started my equation over here.
Oh, okay.
Yeah, sorry, sometimes it just kind of comes together. Alright, so this is our denominator, and those are our numerator, and here's what we're going to see. 16C9, 10C5 times 6C4.
Where did you get 16?
16, 10 plus 6.
Yeah.
Because for the total we're choosing, we have a total of 16 buttons. Okay, and then from there, I'll let you finish the problem, but let's just punch it in your calculator. Honestly, if you got to that point on one of these problems, you've done all the math. The next step would just narrow it down to a single decimal. So I would give you probably, maybe all the credit, but for sure most of it, if not. Okay? Questions on that? Is that working out for you there, Josie?
Yeah. I just have like the whole box left. So.
Yeah, I know. I wanted to do most of the work here, but it kind of took more to write this out. So this is the second to last section, and it's called probability distributions. It will kind of filter down into a single equation that we'll use mostly for this stuff. But it's good to kind of know what these mean and stuff. So what does a probability distribution tell you about an experiment? We talked about this briefly last week, the difference between experimental and theoretical probability. So what's the theoretical probability that I will roll a 1 on a die? Theoretically, it should be 1 out of 6. Is it possible, though, that I roll 10 times and never get a 1?
Yeah.
Okay, so the experimental probability, if I actually sat here and rolled it, could show something different, right? It could show maybe that I have a 0% even chance. So that's kind of what it's referencing when we say experiment. Did we actually do it and we're basing it on data we gathered, or is it purely theoretical? Alright, so Mr. and Mrs. Mason have 3 children. Assume the probability of having a girl is 0.5 and a boy is 0.5. Okay. Which model represents the situation correctly, A or B? So don't shout this out, just kind of look at it for a moment. Okay, what do you think? He says A, I heard B. Any other votes? B, B,
I don't think
Are you guys like doing sign language? I kept seeing you guys do that. Is this B?
it's.
Yeah. I know some sign language.
Don't the odds decrease every time it goes, right?
0.5 times 0.5 is.
Yeah. Okay, so he asked, don't the odds decrease each time? So, first of all, odds is a different concept of probability, slightly. And I guess we need to clarify what you mean.
Well, I know that, like, at first I was on B, right? And then I thought, like, it'd be, like, 0.5 times 0.5, and then it'd be, like, 0.25 or whatever, and then they keep going down until you get, like, the 3 girls or 2 boys or whatever. And then I saw the one above it, and it was kind of, like, 0.25 each, and because there's 4 different outcomes. And I figured it was equal choice for each, or equal odds for each. Or probability.
Well, I guess let's kind of continue to clarify. So, each time you have a kid, it's the same probability of boy or girl.
Yeah.
So I guess it depends how this is being communicated. If we just look out for 3 girls, 0.5 times 0.5 times 0.5, right? So this is not giving any, it's not telling us the answer for how many, for the probability of having 3 girls or any of those, right?
Okay, well then, yeah, that's
We'd have to multiply out. And this one is actually wrong because 0.5 times 0.5 times 0.5 is not 0.25.
These are
0.1. Yep.
Yeah, okay.
So you could do it that way, but it's the numbers are wrong. But you could do it that way. I think it's a little more confusing than this one. So B. We just talked about that. So 3 girls would be 0.125 or 12.5%. Compare the probability that the first child was a boy and they then had 2 girls to the probability that their first 2 children were girls and they had a boy. It's kind of a lot of words. Does the order affect the probability? So here's what it's saying. Their first child was a boy, so we're down this bottom branch, and then 2 girls. So that branch, and then the versus the first 2 children were girls, so girl, girl, then boy. Does the probability change is what it's asking. Okay. What are our 2 outcomes? Like 2 identified possibilities here? Boy or girl. Okay? So what you're going to see as we get into this more is narrowing a probability situation down to an either or. Okay? Either or. And earlier in this unit, you might recall that I said, be careful, just because 2 things exist in a situation doesn't mean their probability is 50-50. You remember me saying that? Okay. This one happened to be, but we are going to deal with strictly either this or that, but that doesn't mean that it's equal probability. So keep that in mind. Let's see. So Tio and Henry are running for president of the student council. You will select a campaign button at random from the box. Do you guys do campaign buttons here? We need a picture of Tom's face on here. Or a button around. Anyway, 3 TO buttons and 3 Henry buttons. You will record the number of TO buttons that you get. What is the theoretical probability distribution for the sample space? Okay. So 3 of each, dude. What is and we're picking, it says you will record the number of buttons that you get. If we just select 1 at random. What is the theoretical, just based on what's in the box? What's the distribution? Meaning, look down here, probability distribution is a function that assigns a probability to each outcome of a sample space. Okay? So what is our sample space? With this button problem. 3 TO buttons, 3 Henry buttons, and then you just draw out some. Remember, sample space is on the front of your packets. I kind of feel like we should put it in your notes too. So maybe let's just grab that and do that. Does anybody have room like at the bottom of the lines, or maybe early on at the top? Any room to shove that in?
I mean, there's one in the county.
Like I have a little room here at the bottom of this one. Okay. What?
Why do you just have an empty box?
I think probably because I didn't want to cram more stuff there. Like I'm about to do. Okay, so grab your packet and tell me what it says for sample space.
Total possible.
Yeah. And it's kind of the description, right? We'll say it this way. The possible outcomes of a probability scenario. So it's a description, maybe a list. So what is the sample space for flipping a coin? That's how many there are, 2 outcomes, but what is the sample space? Heads or tails? Okay. What's the sample space for rolling a die? Okay, so it sounds like we should probably put an example in there. You can put braces around that. You could put braces around H or T as well, right? Maybe I'll just do that here at the end. Okay. And that we could go on. Like, what's the sample space for drawing a card from a card deck? It's huge, right? Like 52 things we'd have to list in there. So often you're not going to list out everything because there are often lots of probabilities or possibilities. Anyway, questions on what sample space is? I guess I just wanted to have it on here so when you make your note card, you don't miss it being on your other. Okay, so you will select a campaign button at random from a box containing 3 of each. You will record the number of TO buttons that you get. What is the theoretical probability for the sample space? And it has this 0, 1. If you just pick one, your options are 0 TO buttons. Actually, I'm just going to write 0 TO. How about that? Or 1 TO. For that one draw, right? You have this box full of 6 buttons. You pull one out. Do you agree that that's your option? You either pull out one or you don't. Okay? That's our sample space. So what is the theoretical probability of 0? What? Okay. What is the theoretical probability that I reach in and I don't get a TO button?
3 out of 6.
Yeah, it's 3 out of 6. And how about the probability that I get a TO button? Also 3 out of 6. So this is a 50-50, right? Why?
Because we have 2 options.
No, that's not why. Be careful. He said we only have 2 options. That is not why the probability is 50-50. Why is it 50-50? Yeah, it goes back to this, right? Okay? If this had said 8 TO buttons, is this a 50-50 now?
No.
So be careful, just because there's 2 options doesn't make it 50-50. Okay? Alright, we're going to move on from that. Okay, so this is something that we have seen, but if we're flipping a coin, right, we're multiplying, this is a 50-50 case, so probability of 2 tails, we would just multiply on our way out. Okay, just keep that. What is this called? Yeah, and it's weighted, even though it's equally weighted, it's a weighted tree diagram because we have the numbers on there, okay? If we are dealing with something else, maybe a die, and we're talking about numbers below 3 or something, then it would not be weighted. Or, I mean, it wouldn't be equal. Excuse me. All right. So we select 2 marbles. Can you guys see the marbles? Okay. 2 marbles from the bowl. For each situation, to find the theoretical probability distribution for selecting a number of red marbles on the sample space 0, 1, or 2. Why is it 0, 1, or 2 in the sample space?
Because you're selecting 2 marbles. Either red or
How many red marbles are in there? 2. So I could pick none, 1, or both of them, right? Okay. And then we'll talk about this in a second. But what is the theoretical probability for selecting 1 red marble? It's for selecting 1 red marble. Yeah. Or 0, or 2. What's the well, I'd have to do 2 draws, but what's the probability for picking 0 red marbles? 3 out of 5. It's no longer 50-50 now, right? How about 1 red marble? 2, okay. And then 2 red marbles, we'd have to pick one. That would change the probability, right? If I don't put it back. Okay. So the whole idea of a distribution in general, the word distribution is talking about kind of the idea of shape of graph data. And we'll see this again in Algebra 2 when we do a statistics unit, this word distribution. So kind of, hopefully it'll stick in there a little bit for you. I think you'll have to try to remember, but I think 7th grade, maybe 8th grade, somewhere in there you guys did. Do you remember histograms? So, like these kind of plots, right? Histograms, okay. Well, you probably created some that had relative frequency data plotted. So let's talk briefly. It's an easy concept to understand. So, suppose you selected a student at random from the drama club and recorded the student's age. Okay. Define an experimental probability distribution on the sample space. What are these numbers? That's our sample space. What do they mean? Those are the ages, right? And so in a high school, you would expect probably 14 to 18-year-old students. Okay? And so experimental probability means we actually went and picked these students, and here's the data that we gathered. Okay? So 14-year-olds, we picked 4 of them, etc. Relative frequency means the percentage of the data that category represents. Okay? How do we find a percentage? And I don't want you thinking like this isn't combinatorics, it's not P of something yet. It's just a percentage of data. So how do we find a percent?
The number divided by the total.
Yeah, the number divided by the total. Okay, so we need the total students. How many is that? 37. Okay? So out of that 37, what is the percentage represented by each age? So relative frequency would say 4 out of 30, excuse me, 37. Can someone, you guys grab your calculators. Let's do this together. Grab your calculators out.
11%.
Well, he said 11, you're saying 10.
Oh, that's 10. That's 10.108. I just rounded up.
So 10.8. Let's round, yeah, let's do mathematical rounding. So that's 11%. Okay, and then 7 out of 37.
Not 10%.
10 out of 37.
27%.
You see, all we're doing is just dividing to get the percentage, right? 7, we already did, was 19. And then 9, 24%. Okay. Add these up. What should they add up to?
100.
They should add up to 100. Double check. I don't think they're going to, but they might. Actually, I think they do.
They do.
They do. It's good job on the rounding. Okay, so they add up to 100. And now we go graph them. Okay? And you notice our graph is set up by age and percentage of the total probability. So this is getting into like, hey, if I go pick one of these kids at random, what is the probability that it will be a 14-year-old? At random, what's the probability that I'll pick a 14-year-old? 11%, right? So 14, and we're going to just make this a bar graph, so this is 11%. And then 19, 16, 19 again, and 24. Okay.
Do the sides have to connect or no?
Okay. So, yeah, I heard you. I was about to answer. So, he's asking, do the bars have to connect? In a histogram, yes. But a histogram is different than this. This looks like one somewhat. So, let's briefly remind you. A histogram, the bars do need to touch if there's data in each bin. So, remember in this, you had intervals. So, it was like, if we did it for this data, it would be like maybe 5 to 10, 10 to 15, 15 to 20, 20 to 25, 25 to 30. So in our data, we would have nobody here, but 14 and 15-year-olds would be here, and then 16 through 18 would go here, right? And so because our data is interval-based, those bars are touching. In this one, it's not that way because this is just 14, right? It's like the category 14. And we're not counting like 14 and a half or whatever,
Are they
right?
allowed to touch?
For this kind of situation, you saying?
Yeah.
Like would it be wrong if you made them touching?
Yeah.
Yes, technically. I guess it depends what you are thinking about your axis down here. Guys, a lot of times this would be a description, right? Like if we go back to the marble problem, I would have red and green. That's all I would have on there. And it would be, for the green, it was 60%, and for the red, it was 40%, okay? So there's no reason to touch those bars because they're not even numerical data, right? For cards, same thing. Like if we said red, or hearts, diamonds, etc., right? There's no reason to touch it. Okay, do you see a shape of this data? And I don't know how much experience you have with this, but if you think about kind of connecting the peaks of this with the line, it's not quite a bell curve, right? A bell curve looks like that. And that's what everybody, when they say grade on the curve, that's what they're talking about. That's perfectly normally distributed data. This isn't quite that way. Like we favor the higher ages. Do you see that? Like more of the data is captured over here than over here. Do you guys see what I'm talking about? Okay. So the probability favors the higher grade levels or higher ages. this is what we mean by a probability distribution. What would it look like if we did a coin flip? Let's just do a very basic example on here. What are our two outcomes? Heads and tails. Again, no reason to connect. What's the probability of heads? If we did theoretical, it's 50%. So each bar would just be up to the 50. Good?
Yeah.
Theoretically. But you could sit here and flip a coin 25 times and never get a heads. I mean, you could. It wouldn't probably happen, but... Okay. How's that? Does that seem okay? Okay. I'm thinking of... I think I'll have you try this with some of your own data, maybe tomorrow, graphing your probability distribution of rolling a die. Let's put this in your notes real quick. And we are out of space, so we'll have to write it in one of these boxes. So experimental probability. Conduct a series of trials and calculate probability on the gathered data. Okay? Experiment means you actually have to do something. With theoretical, you calculate the probability solely based on the given conditions or variables. What have we done mostly in this class? Or in this unit, I mean? Have you actually done anything? No. We have actually done no experimental probability, with the exception of gathering our own data on things like the phones and stuff. Did you guys do that, by the way, that day that I was gone?
We just put in random. At least I
You just did it random.
I just kind of choose.
But we did gather some data on, what was it? Oh yeah, the thumb. Which thumb you put on top. So that was experimental. Okay. So you can do a probability distribution based on either one. So let's write about that. In either case, a probability distribution assigns a function that gives the probability of each outcome in the sample space. Maybe do the little brace thing, reminding you what a sample space looks like. Okay? And then here's kind of the big idea. It's usually shown as a relative frequency bar graph. Okay? And we could set that up, briefly show it as this. That says outcomes. Let me write that better. Outcomes percent. I don't like that one. Just do a better job. Okay. Everybody following so far? One other thing to remind you. Do you remember this? I didn't ask you that. Do you remember doing this in middle school? So relative frequency is the percent of total of each outcome. Okay? And last thing. The shape of the probability distribution. Is a description of where most of the data lies. Okay. So normal distribution would be it's all kind of collected in the center, the biggest bars. What we just saw with those ages was it was kind of heavy to the right. So we would say it's skewed left. We'll talk more about that in our statistics unit. I'm not super concerned about this description right now.
Now it's
65.
no.
Oh, well, one's back. He's going to be. Five minutes. Oh, one's still two. And six. Six is two making a comeback. Oh, four's making no fun. Three going over past four. Oh, and six gets one.
Let's all set up the graph the same way. So you should have your relative frequencies, so you should have your percentage of each outcome. And anyway, I want you to go, you're going to make your graph size-wise so it fits like this. And I'm just going to put percent once so I don't have to write it every time. But just make each successive grid line a percentage. Probably that's enough, right? Did anybody get higher than 70%? Yeah, so that should be fine. Okay, and then down here we're going to do single bar graphs, like not connected. And so in this first one, I want you to leave the first one blank. So don't put anything there. And then in the next space, not on the lines, put the 1. Okay? And then leave a gap, put 2, leave a gap, put 3, etc. So make sure you leave yourself enough room to do it like that. And the reason why is because I want us to be able to compare these directly. So I'll come around and take a picture of yours, and then I'll put them up here and we'll be able to compare them a little bit more directly.